We've been learning about weighted averages and calculating them, and I want us to get to a very important application of weighted averages, and it's called the center of mass. And you're going to see center of mass calculations when you get into your physics classes or some higher level math classes. So these aren't going away, and we're going to slowly scale up and apply it to what we've been learning about weighted averages and using integrals to calculate those things. So first off, what is the center of mass? If you've never heard of it before, like what is it? Well, the center of mass is a position. And that position gets calculated through taking a weighted average. So if you have an object or a system of objects, you go through each part of that system or that object, and at each position, you're going to weight it with a mass. And then you end up summing all of these things up. So you sum all of the positions weighted by their masses, and you divide by the total mass of that object or system of objects. And you end up with a position. And it is a weighted average calculation. And just going beyond definitions here, the best way I like to think about it is just take a metal rod. Okay, and this metal rod has a constant density, and you're trying to move your finger and figure out, where can I put my finger to balance this rod? And if it has a constant density, it's going to be exactly in the center. Exactly in the center. Now, if the density changes, well, then you have to figure out, okay, where do I need to move my finger in order to compensate for that? But wherever you find that balancing point, that is the center of mass of that rod. So that's the way that I like to think about it. Now, we want to eventually talk about center of mass calculations in terms of calculus, but in order to warm us up, why don't we start with something a little simpler? So let's get a x-axis going here. Let's get an x-axis, and we'll call this 0. And what we're going to do, I'm going to drop down a few point masses, and we're going to find the center of mass of these point masses here, this system of point masses. So let's say in orange here, we have a point mass, and it's going to have a mass of 2 kilograms, and its position is at 1 meter. All right. And then another point mass. Let's put this one right here. Say this one right here. This one is 3 kilograms, and its position is 4 thirds. And then lastly, our other point mass is going to be somewhere over here. Let's put it over here. And it's going to be 30 kilograms. 30 kilograms. Whoa. And this one is going to be at 3 meters. So I want you to pause the video and try to find the center mass of this system of point masses, the x-coordinate of the center of mass. All right. Assuming that you've given it a go. Again, we're just going to show that this is a center of mass. This center of mass calculation is a weighted average calculation. So look at this. We're going to say x bar. Okay, so that's how we denote the x-coordinate of the center of mass. And it's going to be equal to, and what did we say? We said we're going to each position and we're weighting it with its mass. So we're going to look at this first point mass. It's going to be at 1 meter, and then its weight is going to be its mass. So 2 kilograms. And then we go through here, and then our next point mass is going to be at this position, 4 thirds, and we're going to weight it with its mass, which is 3 kilograms. I want that in green. In green. There we go. And then lastly, our final point mass, it's at 3 meters, and we're weighing 3 meters, that position, with its mass, which is 30 kilograms. And then all we do is divide by the total amount of mass. So that's going to be 2 plus 3 plus 30. 2 plus 3 plus 30. And what do we get here? Well, in the numerator, that's 2 plus 4 plus 90. So that's 2 plus 4 plus 90. So that's 96. 96. And then denominator, that is 35. So we have 96 35ths. And what is that? I'm not even going to calculate it out. I just want us to estimate here where this is going to be. That's just shy of 3, so maybe it's somewhere right in there. That's going to be x bar. And what do we notice about this? If this is the center of mass of our system of point masses here, And you can notice it is pretty close to this dark blue point mass at 3 meters. That's 30 kilograms. And that's no surprise here. This, remember, is a weighted average. So at this position here, 3 meters, we have a ton of weight going on. Its mass is 30 kilograms. So it does make sense that our center of mass is pretty close to this point mass over here. Now, just one quick note here before we go. If you look in a textbook, you might see some sigma notation explaining center of mass. You might see something like this: x sub I times m sub I, and then you'd have divided by sigma I to n, and then you'd have m sub I down here. Don't let this scare you. This is stating in sigma notation what we took up here. And again, this is a weighted average calculation, so this shouldn't look new. You could think back to, okay, we did something very similar when we talked about stocks a few videos ago. But instead, we're taking positions and we're weighting them with their mass. And this exactly, if we were to extend this out, this would look something like this. We'd have x sub 1, m sub 1, x sub 2, and so forth, and then divided by m naught, m sub 1, plus m sub 2. That's what we would have. That's exactly what we did up here. So don't let this sigma notation confuse you if you're seeing this in a textbook. Now, in the next video, again, this isn't describing any sort of continuous situation. I want to take us to describing a continuous situation and talk about center of mass in that application.